So the dipole moment is the vector having magnitude, the distance multiplied by the charge. That means 2a multiplied by negatively charged electrons will try to move in a direction opposite to the direction of the electric field. So that is the nature of the dipole moment. Right? Okay, unlike the last case we had electric field having direction same as the direction of the dipole moment, but here it is different. Torque we have derived when the axis of rotation is through the midpoint. Okay, the same formula, so it doesn't matter. So what is the axis of rotation? Is the force due to a dipole making some angle θ1 with another dipole making a different. Here in this class we are going to talk about electric dipole. So what is meant by electric dipole? Before we define what an electric dipole is, let us look at all the concepts that we are going to discuss in this class, right? First of all, we'll define what an electric dipole is, alright? And then dipole moment. So this dipole moment is important because all the formulae in this topic are written only in terms of dipole moment. So we'll define what an electric dipole moment is, alright? And then we'll talk about torque on a dipole due to a uniform electric field, alright? Torque on a dipole, and then potential energy related to dipole, alright? Potential energy, and then dipole oscillation, and then due to a non-uniform electric field. We have a force on the dipole, so that we will talk about last, alright? So these are the concepts that we are going to look at one by one in this topic today, alright? Yes. First of all, we will define what an electric dipole is, alright? Yes. A dipole is a pair of equal but opposite charges separated by a small distance, alright? There are two charges, q and minus q, a pair of equal but opposite charges. So these two charges are kept at certain distance, right? So this combination of charges is called by the name dipole, right?
Won't these two charges attract each other?
There must be some mechanism to keep these two charges separated. What if you connect these two charges by a non-conducting rod? In that case, the distance between the two charges will remain the same. See, remember, in a dipole, the distance between the two charges should remain the same, alright? It should be a constant value. The distance between the positive charge and the negative charge of a dipole is constant. Do you understand? Yes. Now, what is dipole? A pair of equal and opposite charges separated by a small distance, a constant distance, alright? This is called an electric dipole. Do you understand? So, we've defined what an electric dipole is. Now, we'll define dipole moment, alright? So, this dipole moment is very important, because in all the formulae we are going to use dipole moment only. Instead of the charge of the dipole, we are going to use the dipole moment, alright? Now this is a dipole having charges q and minus q. What is the charge of the dipole? See, always the net charge of the dipole is 0. Do you understand? Because there is the positive charge and negative charge, so these two add up to 0. So that means the net charge of a dipole is 0 always, okay? But when you say charge of a dipole, you only mean the positive charge q, okay, not the total charge. So the charge of the dipole simply is q. You understand? Q, the positive charge of the dipole, is taken to be the charge of the dipole, okay? Yes. Now the charge of the dipole multiplied by the distance between them, taken as 2a. 2a is the distance between the two charges of the dipole. This distance multiplied by the charge of the dipole is called the dipole moment, alright? Dipole moment is a vector, not a scalar. It is a vector, but the magnitude of the dipole moment, denoted by P, is given by this formula. What is that? The distance between the dipole, the two charges, and multiplied by the charge of the dipole. So that is called the dipole moment, alright? So that means here 2a multiplied by q. So this value is called the magnitude of dipole moment, alright? Yes. Okay.
Why is the distance taken as 2a instead of just a?
See, it doesn't matter whether you take the distance to be 2a or a or d or whatever you want, but the formula here is simply the distance multiplied by the charge, alright? So the distance is 2a multiplied by the charge q. So that is the dipole moment, alright? But generally we take the distance to be 2a because we usually place these two charges symmetrically along the x-axis, having its midpoint at the origin, alright? So one charge q is at the point say a comma 0 on the positive x-axis. The charge minus q at minus a comma 0 on the negative x-axis. So the midpoint is at the origin, right? The center of the two charges. So that is at the origin. Do you understand? So that is why we take that distance to be a and this distance to be a. So the total distance is 2a. Okay. But it doesn't matter. Even if you take the distance to be some d. So the formula will be d multiplied by q. Okay. So in any case, the distance multiplied by the charge. So that is called a dipole moment. Alright, yes. So this is the magnitude of the dipole moment. Okay. That means it also has a direction. Dipole moment is a vector quantity. So it has a direction. So the direction of the dipole moment is simply the direction of the line which joins the negative charge to the positive charge. Alright, so this line joining minus q to plus q. So that direction is the direction of the dipole moment. So the dipole moment is the vector having magnitude, the distance multiplied by the charge. That means 2a multiplied by q here, and also the direction joining the negative charge to the positive charge. So that is dipole moment. So this dipole moment is more important than the charge of the dipole itself. The charge q itself is not very important because the charge and the distance, so the combination, that is what matters in most of the cases. So the charge here is q and the distance is 2a. So this combination, that means the dipole moment, right, 2a multiplied by q. So that is what is used in most of the formulae. So that means, so it's important to know what a dipole moment is, alright, because everything else is written in terms of dipole moment only, alright. So that is about dipole moment, okay. Here we'll find the dipole moment due to a system of dipoles. So here we have charges minus q, and there is a charge 2q. But this doesn't look like a dipole, right? So dipole is a combination of a positive and a negative charge of equal magnitude. So here we have minus q, and there is a charge 2q. But we can split this charge 2q into two parts. One with charge q, the other with charge q. Do you understand? You can combine this charge q with one charge minus q, and the other charge q can be combined with this charge minus q. So that means it will become a combination of two dipoles. So minus q, q, so that is one dipole, and minus q, q, that is another dipole. So we will find the dipole moment due to these two dipoles separately and find the vector sum. So what is the dipole moment due to that dipole? So that is the charge, that is q, multiplied by the distance. So that distance is 2a. Okay, but it has a direction. So what is the direction? So this direction, so this makes angle 30 degrees, right? The total angle is 60. By symmetry, it makes angle 30 degree with the horizontal. So this is the direction of the dipole moment due to the first dipole. Similarly, for the second dipole, so we have the dipole moment in this direction. Again, that makes angle 60 degree. By symmetry, so this vertical components of these two dipole moments, so that will be 0. Because so that will have vertical component in this direction, vertically upward direction. The other one has vertical component in the vertically downward direction. So these two cancel each other. So we only add the horizontal components. Alright, we want to find the vector sum. So the vertical components cancel each other, only horizontal components are added. So what is the horizontal component? Alright, so that angle is 30 degree. So multiply by cos 30 degrees. Do you understand? So 2aq cos 30 degrees, that is the horizontal component of this one. Similarly, for the other dipole moment, so same value, you understand? So 2aq cos 30 degrees. So that means these two if you add, so we will get the total dipole moment. Do you understand? So to find the dipole moment of a system of dipoles, we simply have to find the vector sum of the dipole moments of the separate dipoles. Do you understand? So that's it. So the direction is also important here. So we can't add the scalars, we have to find the vector sum. So here we have taken two dipoles. We can take any number of dipoles. Alright, you find the dipole moment and add the vector sum. Okay, you find the vector sum of these dipole moments separately. So that will give you the total dipole moment. Okay, right.
But why do we learn about dipole? Is there a significance for the combination of two charges?
See, this particular combination of a negative and a positive charge is important because it exists naturally. We are not forcefully putting these two opposite charges together and call it by the name dipole. Let us consider a fundamental structure like a molecule. There are two types of molecules called polar molecules and non-polar molecules. Let us take an example of a non-polar molecule. So a carbon dioxide molecule. What is carbon dioxide molecule? It is a combination of two oxygen atoms and one carbon atoms like this. Now these two oxygen atoms are negatively charged. Not exactly negatively charged due to its electronegativity, so they have the tendency to be more negative than positive. Let us consider these two oxygen atoms to be negatively charged and this carbon atom is positively charged. Now what is the center of the positive charge here? So that is exactly in the middle, right, midpoint, because that is only one atom. Now what is the center of the negative charges? So that is also in the middle because these two oxygen atoms are symmetrically placed. So the center of the negative charges is also the same point in the middle. That means the position of positive charge and position of negative charge, so these two coincide. That means it is not a dipole. What is dipole? The negative charge and the positive charge should be separated by a distance. But here, so these two have the same position. They coincide. So that means it is not a dipole. So this is called a non-polar molecule, right? So non-polar molecule, the center of the positive charge and center of the negative charge, these two points coincide. Do you understand? For example, this carbon dioxide molecule. Alright? Yes. Now we'll take an example of a polar molecule. This is a water molecule, H2O, 2 hydrogen atoms and 1 oxygen atom. So this negatively charged oxygen atom has center at that point only, because only one atom, and these two positively charged hydrogen atoms have center at the midpoint, right? That means the center of the positive charges, okay, so that is at some position which is different from the position of the negative charges. That means this positive charge and negative charge are separated by some distance, so this behaves like a dipole. Do you understand? So these two charges, right, the negative charges and positive charges are separated by some distance, so we can consider that to be a dipole. So this is what we call by the name polar molecule, right? Polar molecule is more like a dipole. So this exists naturally. We are not putting these two charges together, a negative and positive charges together, and call it by some name dipole, because a very fundamental thing like a water molecule behaves like a dipole. Do you understand? Not only that, you take an example of an atom. An atom contains nucleus which is positively charged because of the protons. So what is the center of these positive charges? So that is exactly at the center of the atom, because nucleus is at the center of the atom. So the positive charges are concentrated at the center of the atom. Okay, now these negatively charged electrons are orbiting around the nucleus, but what is the center of mass of these electrons? So that is also at the center only because of the symmetry. So there are many electrons. This is electron cloud. Okay, so there are many electrons, but the center is at the center of the atom only. Okay, right. Now that means it is not a dipole, because the center of negative charge and positive charge, so that coincide, right? These two coincide. So that means it is not a dipole. So because the negative charges and positive charge, they are not separated by some distance. Okay, now the same atom is placed in an electric field. So when this atom is placed in an electric field, what will happen? These electrons, the negatively charged electrons, will try to move in a direction opposite to the direction of the electric field. So that is the nature of negative charge, right? So negative charges will try to move in the direction opposite to the direction of the electric field. So that means it is no more a symmetric structure, right? Like that means the center of these negative charges is now off center. Okay, that means the negative charges are concentrated at a point which is not same as the center of the positive charges. So now it is like a dipole. Do you understand? So there is a negative charge, there is a positive charge separated by some distance. So this is like a dipole now. Do you understand? So each atom has the potential to become dipole. So that is why dipole is important. But we don't get into these details, right, of subatomic particles, right? We will just learn about the general behavior of dipole. Okay, so now we have learned some basic points about dipole. So what is dipole and dipole moment, and also some significance of dipole. So this is the first point about dipole that you have to know. Okay, now so that is a simple point. The next one is about the electric field due to the dipole, right? So the first one here is we'll find the electric field due to a dipole. So we know that the net charge of a dipole is 0 because there is a positive and negative charge of equal magnitude. That means the total charge of a dipole is 0. But the electric field due to the dipole is not 0 because these two charges are separated by some distance. That means the effects of these two charges at some point in space are different. Do you understand? Because the distances are different, that means the electric field due to the two charges are different, so they don't cancel each other. So we will find the electric field due to this dipole at some point on the axis. So what is the axis? Simply a line joining these two charges. So we have a point on the axis, we will find the electric field due to this dipole at that point. So what will you do? Simply we will find the electric field due to the charge q, and we will also find the electric field due to the charge minus q and find the sum. So that will give you the total electric field. Okay, so let us find one by one the electric field due to the charge q. Okay, so the total electric field here is, so E. Okay, we only take the magnitude, okay, taking the horizontal direction, this direction to be positive. So what is the electric field due to that charge q? Okay, now we have taken a point at a distance r from the center, okay, midpoint. Okay, from the midpoint, that point is at a distance r. Okay, so that means what is the electric field due to the charge q? So that is kq divided by the distance squared. But what is the distance there? From the center, the distance is r, but the charge q is already at a distance a from the center. So that means the required distance is r minus a squared. Do you understand? So this is the electric field due to the charge q, but that is in the positive direction because that is a positive charge. So that means it will be in that direction, okay, forward direction. So that means kq divided by r minus a squared. Done. Similarly, we'll find the electric field due to the charge minus q. So that is minus, right, negative direction, because that is a negative charge. so the electric field will be towards that charge. That means in the negative x direction. So minus, and then write the magnitude of the electric field. So that is kq divided by the distance squared. But what is the distance? So that is a from the center and then plus r. So a plus r here. So r plus a squared. Okay, so that is the total electric field. That's all. Okay, now let us simplify this. So kq divided by, so this will be, okay, so if you multiply you get r squared minus a squared the whole square, and then this is r plus a squared minus r minus a squared. So if you do the subtraction, r squared that gets cancelled, a squared gets cancelled. So this is 2ra, this is again 2ra, so that will be 4 times a r. Do you understand? So after simplification we get simply this one, 4ar. That's all. So that is the electric field. Do you understand? So but we can write it as, see, 2a multiplied by q. What is 2a multiplied by q? So that is called a dipole moment. So we have the formula for dipole moment P. So that equals the distance 2a multiplied by the charge q. Alright, so that is the formula for dipole moment. So P equals 2a multiplied by q. So here 2a multiplied by q, so that can be written as P. So this becomes a 2k and then 2a multiplied by q. So that is taken as P. Then that r divided by, so this r squared minus a squared the whole square. Okay, so that's all. So this is the electric field. So that's all. That is the formula for the electric field due to the dipole at a point on the axis. Okay, done. All right. Yes. Now we will also write a particular case. So this is important. A short dipole. What is meant by short dipole? A short dipole means the distance between the charges of the dipole is very, very small, okay, compared to the distance involved here, right? For example, here the distance is 2a, so that 2a is very, very less than the distance r, okay? So a is very, very less than r. Or we can say that a is approximately equal to 0. A cannot be 0 because it's a dipole, so but a is very close to 0, okay? The distance between the two charges is very small, okay, compared to the distance r, okay? So that is called a short dipole. So this is important, right? Short dipole is important. So for short dipole, so what will be this formula? When this a is very, very less compared to the distance r, that means what is r squared minus a squared? So this r squared minus a squared can be approximately taken as r squared only, okay, because a is very small. So that means if you subtract that from this very big value r, so that will have no effect. So r squared minus a squared is approximately equal to r squared only. So what will the formula become? So that is E equals, so 2kpr divided by, this is only r squared to the power 2. So that means r to the power 4, already there is r. So if you cancel that, so we'll get 2kp divided by, this is r to the power 4, 1 r gets cancelled, so it is r cube. Alright, so this is the electric field due to the short dipole at a point on the axis. Okay, so this is the formula, so that you have to remember. Okay, electric field due to a short dipole. Okay, done. But what is the direction of this electric field? So electric field is a vector. So it has magnitude this value, but it also has the direction. Okay, electric field. What is the direction of the electric field? That is in the positive x direction, right? That is same as the direction of the dipole moment, because the dipole moment has direction joining the negative charge to the positive charge. So that is the positive x direction. So this also has the same direction. So that means the electric field has the same direction as the direction of the dipole moment in this case. Which case? The point is on the axis. In that case, the electric field has the same direction as the direction of the dipole moment. Okay, so that means this has direction. So direction of E is same as the direction of the dipole moment. Okay, P vector. Okay, so this is also important. So remember this. So two things you have to remember: the magnitude of the electric field and also the direction of the electric field. Okay, at a point on the axis, the magnitude has value, this one, 2kp divided by r cube for a point on the axis. Okay, and also it is a short dipole. Okay, only for a short dipole. If it is not a short dipole, in a general case we have to use this formula. Okay, for a short dipole we have to use this. In most of the cases you will get we'll have to use this formula only. Okay, 2kp divided by r cube for a short dipole. And also remember the direction of the electric field. So that is same as the direction of the dipole moment. Okay, yes, done. So this is the first case of electric field. So what is this case? We find electric field due to a dipole at a point on the axis. So that has formula this one. Is that okay? Yep. Here we will find the electric field due to a dipole at a point on the equatorial plane. That means the perpendicular bisector plane. So that is a plane passing through the midpoint and perpendicular to the axis. We have a point on this plane. We have to find the electric field due to this dipole at that point. Okay, so let us find it. By the same method, we will find the electric field due to these two charges separately and find the sum. The vector sum we have to find. So in the last case, we've just added the magnitudes because the electric field due to these two charges, Q and minus Q, so they have the same direction, at least the opposite direction. So we've simply added the magnitudes. So one of them has negative direction, so we've added them. But here they have different directions. So the electric field due to the charge Q, so that is E1 vector, that is in one direction. Alright, away from the charge, because Q is positive, away from the charge. And similarly, we have electric field due to the charge minus Q towards the charge. Okay, E2 vector, we have to find the vector sum. Do you understand? So let us find the electric field due to the first charge Q. Okay, so E1 vector. So E1 vector. So that is, first let us write the magnitude, okay, KQ divided by R squared. So KQ divided by R squared. R is the distance. So what is that distance? So that is a right angle triangle. So we can use Pythagoras theorem to find that distance. Okay, A squared plus R squared. You understand? A here, R. So A squared plus R squared, square root, the square of that. So which means it is A squared plus R squared. That's all. So this is the magnitude of the electric field. Now we have to find the vector form. So that means you also have to multiply the unit vector in the direction of E. Okay, now this angle is taken as theta, so theta, that is also theta. So this E1 vector makes angle theta with the horizontal, okay, with the negative x-axis. So that means you have to take the projection. So what is the projection in the horizontal direction? That means that value multiplied by cos theta, right? Cos theta minus I cap, because in the negative x direction. So cos theta minus I cap. So which means, so this is minus cos theta I cap. Similarly, vertical projection. So vertical projection is in the upward direction. So that means it's a positive j cap. That is the unit vector. So that means it is sin theta j cap. Do you understand? So this is the unit vector in the direction of E1 vector. Do you understand? This is only the magnitude. So multiply that by the unit vector in the direction of that vector. Okay, E1 vector. Alright, so that's it. Now we can also do this question without using vector form, because we find the E1 vector and similarly we will find the E2 vector and we have to add them. But this E1 vector has a vertical component in the upward direction. E2 vector has a vertical component in the downward direction. So the vertical components cancel each other. You simply have to find the horizontal component. Do you understand? But we have not used that method. We have written the vector form properly and then finally we can add that. Okay, so we can avoid this sin theta j cap if you want. Okay, because anyway that is going to get cancelled. So now we will write separately. So E2 vector, the electric field due to the charge minus Q, that is in this direction. So that means, so that will have the same magnitude, because Q, the magnitude of the charge is same. So that has the same magnitude. So KQ divided by, so A squared plus R squared. Okay, and then the unit vector. So what is the horizontal projection? So that is same thing, right? Cos theta I cap minus I cap. Okay, in the negative direction. So minus cos theta I cap. Minus cos theta I cap. And then the vertical projection. So that is sin theta minus j cap, because it is the downward direction. Okay, this is E2 vector. So that has the vertical component in the downward direction. That means minus sin theta j cap. So we have to add these two values. Okay, but if you add this, vertical components will cancel each other. Okay, so directly we could have written the horizontal components only, but anyway we have written both the components and then add this value. Now we want the required, the electric field. The total electric field is the sum of these two. So E1 vector plus E2 vector. Okay, so add these two. So this will be, this will get cancelled, sin theta minus sin theta. This is 2 times. Okay, minus cos theta minus cos theta. 2 times minus cos theta. So that means it will be minus 2KQ divided by this value, A squared plus R squared multiplied by cos theta. Okay, I cap. So that's all. So this is our required electric field vector, right? The resultant of these two electric field. Okay, that is our answer. Now we will write only the magnitude. So what is the magnitude of this? Simply E. So that is 2k, I'm not writing the negative sign, so this is 2kq divided by, this is r squared plus a squared multiplied by cos theta. Cos theta value can be written, right, in terms of the other known values, because again it is a right angle triangle. In that right angle triangle, the value of cos theta is this adjacent side. The base here is a divided by the hypotenuse, which is a divided by, so that is square root of r squared plus a squared. So that is the value of cos theta in that triangle. Okay, now again this is 2aq, okay, this is 2 times a, that is the distance between the charges multiplied by the charge. So that is same as the electric dipole moment. Do you understand? So distance multiplied by a, 2aq is the dipole moment. So that can be written as simply p, so which means it is kp. That's all, kp divided by, this is r squared plus a squared, this is r squared plus a squared to the power 1 by 2. So if you add this, we'll get r squared plus a squared to the power 3 by 2. So that is our required electric field. Okay, so this is the formula for the electric field due to the dipole at a point on the perpendicular bisector. Okay, done. That's it. Now like we did earlier, so here also we will write the particular case for a short dipole. For a short dipole, so what does it mean? So the value of a is very small, okay, compared to the distance r, okay, that is called a short dipole. So in that case, r squared plus a squared value is what? Because a is very small, okay, so smaller than this value of r, right, much smaller compared to the value of r squared plus a squared can be approximated as r squared only. So we can take r squared plus a squared value to be approximately equal to r squared only. Okay, what will this become? So we'll get E equals kp divided by, this is r square only, r square to the power 3 by 2, so that is r cube. So kp divided by r cube. So that's all. So that is the formula for electric field due to a short dipole. Okay, so that's all. So this is the formula that you have to remember. Okay, this is the electric field at a point on the perpendicular bisector. But what is the direction of this electric field? So the direction is this, okay, in the negative x-axis direction. But what is the direction of the dipole moment? That is in the positive x-axis direction, which means here the electric field has direction opposite to the direction of the dipole moment. Okay, unlike the last case. In the last case we had electric field having direction same as the direction of the dipole moment, but here it is different. So this also is important, we have to remember. So the direction of this E vector, the electric field, is equal to opposite to the direction of this P vector. Understand? So this you have to remember. So in these two cases, the direction is either parallel to the dipole moment or anti-parallel, right, opposite direction. Okay, so that's all. So this is one thing. So these are the two things we have to remember. This is electric field due to the dipole at a point on the perpendicular bisector, but this is a particular case where the dipole is considered to be a short dipole and the direction is opposite to the direction of the dipole moment. Okay, so this is the second case of electric field due to a dipole, so where the point is on the perpendicular bisector. Is that okay? Yep. This is the most general case where we'll find the electric field due to the dipole at any point in space, okay, not necessarily on the axis or on the perpendicular bisector. So this time the point can be anywhere in space, but here we'll only consider the case where this is a short dipole, okay, not a general case, a short dipole, but the point can be anywhere in space. Okay, so say the point A is here at a distance r from the center, right, from the midpoint the distance is r. This radial vector, right, OA is the radial vector that makes angle theta with the dipole moment. So this is the dipole moment horizontal. So this radial vector makes angle theta with the horizontal. Okay, so now we have the point A. We will find the electric field due to this dipole at that point. Okay, now as a particular case, if theta is 0, so what if theta is 0? If theta is 0, so that radial vector becomes horizontal. So that is the first case we have done. So where the radial vector has the same direction as the dipole moment. So that is the first case, we have the formula for that. Similarly, if the angle theta is 90 degrees, that also we have done already. So that is the second case when the point is on the perpendicular bisector. So that is also done. But this time theta can be anything, right? Not necessarily 0 or 90 degrees. Okay, so what we are going to do is we'll consider two components of the dipole. Okay, so this dipole is horizontal, but that makes angle theta with the radial vector, but we want the angle to be either 0 or 90. Then we have the formula. So we want the angle between the dipole moment and this radial vector to be either 0 or 90 degrees. Only then we can use the previous formula, right? Yes. What we are going to do is we take the component of this P in two directions. One in the radial direction. In that case, the angle becomes 0. So if you take the component of P in the radial direction along the radial vector, so then the angle between the radial vector and dipole moment becomes 0. So that is the first case. We also take the component of this P in the perpendicular direction. So if we take the perpendicular direction to the radial line, so then also we have a formula, right? The second case. So these two cases we have to combine. Do you understand? So let us first find the component in the horizontal direction, okay? In the direction along the radial vector, okay? In the radial direction. So we'll find the electric field in the radial direction. So what is the formula for the electric field? That is taken as say E1 vector. So that equals, what is the formula for the electric field when the point is on the axis? So that has the formula 2kp divided by r cube. That is the first formula we have derived because this is a short dipole. So we can use this formula 2kp divided by r cube. Okay. But we should not use this formula because P is not parallel to the radial vector. You understand? So this P makes some angle theta with the radial vector. So what we have to do is we have to take the component of P in the radial direction. So what is the component? P is horizontal, but this angle is theta. So we have to take the component of P in that direction. So that is this P multiplied by cos theta. So that is the component, right? Multiplied by cos theta. So this P should be multiplied by cos theta. So this is the component of P in our required direction. What direction? So the radial direction. So now once you have taken the component, then the electric field, then the radial vector and the dipole moment have the same direction. So first formula. So that is the first one. 2kp, but instead of P cos theta, the component multiplied by divided by r cube. Done. So this is the electric field due to the component in the radial direction. Okay, done. Now similarly in the perpendicular direction. Take the component of P in the perpendicular direction. So if you take the component of P in the perpendicular direction, then that point will be on the equatorial plane. So that means on the perpendicular bisector. Then it is the second case. So what is the formula in the second case? So E2 vector. So what is E2 vector? So that is when the point is on the perpendicular bisector. So that means what? The dipole moment and the radial vector are perpendicular. So that is the second case. So what is the formula there? So 2 is not there. So that is kp divided by r cube. That's all. This is the formula, okay, when these two are perpendicular. Okay, done. Again, you should not use this P. We have to take the component of P in the perpendicular direction. So what is the component of this P in the perpendicular direction? So that is P sin theta, because this angle is theta, this is 90 minus theta. So P sin theta is our perpendicular component. So instead of P, we have to use P sin theta. Do you understand? That's all. These are the two components of the electric field. Okay, the required electric field, two components in the two mutually perpendicular directions. So E1, E2. Do you understand? Now we have to take the resultant. See, simply the formula is 2kp by r cube. But P here is the component of P in our required direction. Here also kp divided by r cube. But here the P is the component in the perpendicular direction. Okay, done. Okay. Now our net resultant. Okay, so that is E. The magnitude. So required magnitude is, so E1 vector plus E2 vector. Right? So that means the magnitude is square root of, because these two vectors are perpendicular. So E1 square plus E2 square. Correct, that's how we take the magnitude. Two vectors are in the perpendicular direction, mutually perpendicular direction. So the magnitude of the resultant is square root of E1 square plus E2 square. So this square plus this square. That's it. So let us simplify this. So that becomes, so we can take out some common factors. Kp divided by r cube. So Kp divided by r cube. And then what is left? 2 cos theta. Square of that. Okay, 2 cos theta. The square. And then sine square theta. So this will become square root of 2 cos theta square, which means 4 cos square theta plus sine square theta. Okay, so that's all. So if you simplify that, we will get the value of E. So that is equal to, so Kp divided by r cube Okay, multiplied by, see 1 cos square theta plus sin square theta, that will become 1 because sin square theta plus 1 cos square theta, that is 1 plus remaining 3 cos square theta. So that will be square root of 1 plus 3 cos square theta. So that's all. So this is our required electric field, the magnitude of the electric field. Okay, so that's all. So this is the answer, the magnitude of the electric field due to this dipole at some random point. Okay, yes, that's all. Now what is the direction? So the direction also we need, right? That E vector makes some angle with the radial vector. So that angle, say some alpha. So if that angle alpha is known, so we have to find that angle alpha. Okay, what do you have to find? So the direction, see that E vector makes not angle alpha with the horizontal. Already this vector E1 vector makes angle theta with the horizontal, and with that E1 it makes angle alpha, that means theta plus alpha. So theta plus alpha is our required angle. So the direction is simply theta plus that angle alpha. But that angle alpha is what? That we can easily find, right? So tan inverse of, because so that is the horizontal component. The horizontal component is E1. The vertical component is E2. So that means, so this is theta plus tan inverse. Theta plus tan inverse of E2 divided by E1. Correct or not? Two components, vertical and horizontal component. So tan theta is equal to vertical component divided by horizontal component. So tan inverse of E2 divided by E1. Okay, done. So that's all. So this is our required answer. But what is E2 divided by E1? The magnitude, because we know E2. E2 vector has magnitude, this one, Kp sin theta divided by r cube. Similarly this one. So if you divide, you will get the required answer. So that will be simply, so theta plus tan inverse of, so E2 divided by E1. So what is this value? So this is this 2. Okay, then sin theta divided by cos theta, that is tan theta divided by 2. So that's all. So this is the answer. So tan theta divided by 2. So that's all. So this is also formula you have to remember. So theta plus tan inverse of tan theta divided by 2. So that is the angle made by the resultant vector with the horizontal. Okay, and also it has magnitude Kp by r cube root 1 plus 3 cos square theta. You understand? So that's all. So this is the general case where the point can be anywhere in space. Now we find the electric field due to the short dipole. So this has formula, this one. Okay, so if you want, you can write the value, say alpha, right? Tan alpha. So we got this because of this, right? Tan alpha equals E2 divided by E1. Okay, tan alpha, okay, is E2 divided by E1, right? Perpendicular component divided by the horizontal component. So E2 divided by E1. So that's also, from that we can write this one. So this is the answer, right? The electric field due to a short dipole at any point in space. Okay. Yep. We'll find a torque on a dipole due to a uniform electric field. There is an electric field in the horizontal direction. Now this is a uniform electric field. That means at any point in space, the value of electric field is same, right? Constant value. In this electric field, we place a dipole. So this dipole makes some angle theta with the horizontal. This means the angle between the dipole moment and this electric field is theta. Okay. Now we will find the torque on this dipole due to this electric field. First of all, we'll find the force. So what is the force due to this electric field on this dipole? So let us find the force first. Force on this dipole. Okay. So what is the force? So if the electric field is known, what is the force? So there is an electric field E. So let us find the force on the charge Q first. Okay. So what is the electric force? So the force here is the electric field multiplied by the charge. So that means the force on the charge Q. So that is the charge Q multiplied by the electric field. Okay. So this is the formula for force. Charge multiplied by electric field. Okay, done. But what is the direction? Because this charge Q is positive, the force on that charge is in the direction of the electric field only. That means a positive direction. So the force on the charge Q is in this direction. Okay, done. Now similarly, we'll find the force on the charge minus Q. Okay, so that will be in the opposite direction because it is a negative charge. It will be in the direction opposite to the direction of the electric field. That means minus QE. So that's all. That is the total force. This is the force on the charge Q. This is the force on the charge minus Q. So this total force is 0. That means the total force due to a uniform electric field on a dipole is 0 always. Do you understand? Uniform electric field and the total force is 0. Okay, so now the total force is 0, but that doesn't mean the torque is 0, right? So there will be some rotational effect, right? So total torque also we will find. So let us find the torque. Okay, so what is the formula for torque? So that is the force multiplied by the perpendicular component, right? The distance, the perpendicular distance, okay? Or if you write it in the vector form, so that is this d vector or r vector, so that is the vector, right? Radial vector multiplied by the cross product with the force vector. Okay, so d cross f, or we can simply say that the magnitude, so this magnitude, so this is only this is the vector form, so we just need the magnitude. Magnitude is the force multiplied by the perpendicular distance. The force here is already known, so that is QE magnitude, right? QE multiplied by the perpendicular distance, so that distance is A, right? From the midpoint to that line along the force, so that is A. Now we want the perpendicular component, so that is A sin theta, because this horizontal angle is theta, so this is sin theta. So that means, so our required value is A sin theta. Okay, so this is the torque on the charge Q only. Okay, we also have to find the torque on the charge minus Q. But what is the direction of this? So this direction is, see, this is in this direction. Okay, the force is in this direction, which means this rotational effect is this, the rotation. That means it is inward force. Okay, so D cross F. So D is this and F is this. So that means it is a inward direction. Do you understand? So right hand rule we know. So this is D vector, F vector. So D cross F is inward vector. So this direction is the inward direction. Okay, done. Now we will also find the torque on the charge minus Q. Okay, what is that charge? Torque, so that will be same thing. Force is QE magnitude. QE multiplied by the perpendicular component of the distance. So that is again same thing, right? A sin theta. But what is the direction? Again it is in this direction. So rotation. So that is inward direction again, right? Inward. So this also has the same direction. So both the directions are same. So it is simply plus, not minus, plus. Do you understand? So both have the same direction, so we can simply add it. So but the magnitudes are same. QE A sin theta. So that's all. So that will be 2A Q E sin theta. Do you understand? So that's all. But 2AQ can be written as distance multiplied by charge. So that is the formula for the dipole moment. So this is P, the dipole moment. So this is P multiplied by, so E times sin theta. So that's all. So this is the formula for torque, right? Torque on a dipole due to a uniform electric field E is simply PE sin theta. That's it. So that's also, that is the formula for torque. Okay, but we can also write it in the vector form. So this torque is a vector, so that equals, so PE sin theta can be written as what? So P vector cross E vector. So this is a cross product, right? Magnitude of P, magnitude of E, sine of the angle between them. So P cross E. So this can also be taken as a formula for the torque due to a uniform electric field E on a dipole. Is that okay?
Can we write it as E cross P?
See, this direction is important. If you just want magnitude, whether it is P cross E or E cross P, so both will give you the same value. But if you want the direction also, so P cross E, okay, not E cross P. What if you take E cross P? E cross P. So that will be in the outward direction, right? E, P. So E cross P will be in the outward direction. But actually this is inward direction. We have taken the inward direction to be positive direction. That's why these two values are positive. So, but if you write E cross B, that will be in the outward direction. So opposite to the direction we have taken. So that means P cross E is the correct order. You understand? So P cross E, okay, that is the torque vector, or the magnitude of the torque is simply given by PE sin theta. Is that okay? So that is one formula, right? The torque due to a uniform electric field, okay, on a dipole. Okay, as a particular case, if you want, if you take theta equals 0, when theta is 0, so that means what? It is horizontal. Okay, theta is 0, which means the direction of dipole moment and the electric field, okay, are same. Okay, now theta is 0 or even 180 degree. Okay, so it is 180 degrees. So in both the cases, the electric field is so the dipole moment is horizontal. You understand? So one is the same direction as the electric field, one is in the opposite direction. In any case, so sine 0 or sine 180 degrees, so both are 0. So that means the torque is 0. So this implies torque is 0. That means it is in equilibrium. Do you understand? Rotational equilibrium. Okay, so no movement, right? The rotational equilibrium. So theta is 0 or 180 degrees. So the torque is 0. That means it is in equilibrium. Do you understand? Okay. So that's all. That is a particular case. So generally the torque is Pe sin theta. Do you understand? This is only due to a uniform electric field. If it is not uniform electric field, what will happen? Then this total force is not 0, because the force acting on the charge q, the force acting on the charge minus q, they are not same, because the force is the electric field is different at different points. But here both the electric fields are same, q multiplied by same E, right? Here also same E is multiplied. So that is why the total force is 0. The force itself will not be 0 if the electric field is not uniform. That case we will take up later on. But here in this case we only consider uniform electric field where the total force is 0. Only the torque is non-zero. Okay, the force is 0 but the torque is non-zero, which has value Pe sin theta. Okay. Yep. We'll find the potential energy of a dipole due to a uniform electric field. In the last case also we had a uniform electric field and we found the torque on a dipole. Now we will find the potential energy. Okay, now initially this dipole makes angle some theta 1. Okay, and then the angle is increased, now it becomes theta 2. So now there will be a change in potential energy. So that change in potential energy is what we need to find. So the change in potential energy, so that equals, so that is a formula, right? So work done by the external force, so work done by the external, so not force here, torque, so torque due to that uniform electric field. Okay, because total force is 0, so the torque, the work done by the external torque, so that is the potential energy. Okay, now that equals, what is the formula for the work done? So that is the torque multiplied by d theta. Okay, just like force multiplied by displacement. Okay, that is for linear motion. So here it is rotational motion. So torque multiplied by d theta. So that is the change in potential energy. Now to find the potential energy, you have to do the integration. So this is du. Now we want to find u. So integrate. So integration of du. So that equals, so integration of this torque. So torque we formed just now. Okay, so that is Pe sin theta. D theta. So that is torque. Now, so initially the angle was theta and it changes to theta 2. So theta 1 to theta 2. So that is the range. Okay, the limit of the integration. Okay, so that's it. Now this du, so that will become u. Again from theta 1 to theta 2. So that means, so u of theta 2 minus u of theta 1. So that is the change in potential energy. So that equals, so let us do the integration of this. So this will become minus Pe cos theta. So from, so this is the limit of integration, so that is theta 1 to theta 2. Okay, yes. Now so let us do the substitution here. So this will become P, so minus of cos theta 2 minus of minus cos theta 1. So that is written as cos theta 1 minus cos theta 2. Okay, so that's all. So this is the change in potential energy. Okay, now that's it. So this is u of theta 2 minus u theta 1. Okay, right. Now see, now take this angle theta 2 to be 90 degrees. Okay, so 90 degrees. So initially it is at 90 degrees. So finally it is at 90 degrees. So take this value of theta to be theta 2 to be so 90 degrees. Okay, yes. Now you take this theta 1 to be theta only. Okay, theta 1 is taken as simply theta. Now what is this value? And also we assume that the potential energy at 90 degrees. Okay, so when it is at 90 degree, which means perpendicular, at that position the potential energy is taken to be 0. So we can assume at any point whatever potential energy you want, right? It is only relative. So related to that, what is the potential energy at other points? Okay, now we assume the potential energy when this is perpendicular, so that potential energy is assumed to be 0. So that means, so u of theta 2, so that is 0. Okay, now u of theta 1, so that is u of theta. So let us do the substitution. So what will you get? So that is, so this becomes 0, 0 minus u of theta. So that equals, so we have taken this u of 90, which means theta 2 is 90. So just substitute this theta 2 value, 90 degrees. So cos 90 is 0. So that means P cos theta. Okay, so that means our potential energy when the angle is theta, so that equals, so minus P cos theta. So that's all. So this is the potential energy when this dipole makes angle theta. Do you understand? Assuming the potential energy when it is perpendicular at 90 degree. So that potential energy is assumed to be 0. So then at angle theta, the potential energy is simply this one minus Pe cos theta. Okay, yes. Now, so we can also write this as minus Pe cos theta can also be written as, this is a dot product, right? So this is P vector dot E vector. So that is a dot product, right? The scalar product, right? Pe cos theta can also be written as P dot E. So that's it. So this is the formula for the potential energy. So we assume that the potential energy when this dipole makes angle 90 degree with the electric field lines, so that is 0. Okay, then at any point theta, the potential energy is minus Pe cos theta. Okay, yes. Now let us take a particular case. Okay, what will happen when theta is equal to 0? So when theta is 0, at that point what happens? So the potential energy at 0, okay. So that equals, so minus Pe cos 0, cos 0 is 1, so that means minus Pe. That is the minimum potential energy. Do you understand? So this is the minimum potential energy because we have substituted the maximum value of cos theta, which is 1. So this is the minimum potential energy. So when the potential energy is minimum, what does it mean? So when the potential energy is minimum, so that is when it is in equilibrium, right? It is in equilibrium, but particularly it is in stable equilibrium. So if you remember all the concept of this equilibrium, stable equilibrium and all that. So because we have already seen that, so when theta is equal to say 0, when theta is 0, this will be horizontal. Okay, the dipole is horizontal. Okay, that means the angle with the electric field line, so that is 0. So that means the torque is 0. When the torque is 0, that means it is in equilibrium. But particularly when the potential energy is minimum, so that is called a stable equilibrium. Okay, stable equilibrium. What if theta is equal to say 180 degree? Okay, theta is 180 degree, so u of 180 degree, so that equals, so that is, so cos 180 degrees, so that is negative 1, so already there is a negative sign, so that is P, so that will give you the maximum value. So that means it is unstable equilibrium. But what is stable equilibrium, unstable equilibrium? See, when it is stable equilibrium, so when you disturb that equilibrium position, it will try to restore, okay, to the same position. Okay, so there will be a restoring force towards the center. Okay, but if it is unstable equilibrium, when you disturb that position, so it will not get back to the same position again. So this is the stable equilibrium, unstable equilibrium. We will talk about that in detail when we discuss the oscillation, right? Now here, stable equilibrium when this angle theta is 0, horizontal. Again, when theta is 180 degrees, so that is unstable equilibrium, that is in the opposite direction. Do you understand? So this is the formula for the potential energy, okay, at theta equals minus Pe cos theta, okay, and also the potential energy when theta is 90 degrees, so that is taken to be 0, okay. So that is about the potential energy of a dipole in a uniform electric field, okay. Here also we have a dipole placed in a uniform electric field. In the last case we have seen that when the angle is 0, that means this dipole moment makes angle 0 with the electric field lines. In that case, so we have a stable equilibrium. So what does it mean? So when you disturb the object in the stable equilibrium position, so that will have an oscillatory motion. So that oscillatory motion is what we are going to talk about. Alright, yes. Now we have seen that the torque when it makes angle theta is, so the torque equals, so minus Pe sin theta. So we have taken minus, I am taking the outward direction to be positive. So that means this will be minus Pe sin theta. Okay, so minus Pe sin theta is the torque. Now we will take this angle theta to be very small. So theta is very small. So when you take theta very small, only then it will have that simple harmonic motion. Okay, so theta is taken to be very small, so slightly disturbed. Now when this theta is very small, so we approximately take this sin theta to be theta only, right? So this approximation we have done in many places, right? So sin theta can be approximately taken to be theta only. Okay, so that means this tau will become minus P theta. So that means the torque is proportional to the angle theta. So what does it mean? So that means it is in simple harmonic motion, right? So angular simple harmonic motion, right? Theta, right? The rotational motion. So this torque is proportional to the angle theta. So that is in simple harmonic motion. So that means, so what is the formula? So the torque can be written as, so the moment of inertia multiplied by the angular acceleration. Just like the force can be written as the mass multiplied by the acceleration. Mass times the acceleration is the force. So torque is the moment of inertia multiplied by the angular acceleration. So that equals, so minus P multiplied by theta. Okay, so that means the angular acceleration is given minus P divided by I, the moment of inertia multiplied by theta. So this is the angular acceleration, so that is proportional to the angle theta. Okay. Now, so we have the formula alpha, the angular acceleration equals minus omega square theta, right? So that is the formula for the simple harmonic motion, right? So the angular simple harmonic motion. So alpha is minus omega square theta. We can compare these two and find the value of omega. Once omega is found, then we can write the time period. So the time period of the simple harmonic motion T is given by the formula 2 pi divided by omega. 2 pi divided by omega. Alright, that is the formula, but omega can be found using this formula. So that if you simply substitute here, so you will get the answer 2 pi multiplied by omega. So omega is what? The square root of I divided by the root, right? Square root of I divided by PE. That's it. The square root of I divided by PE. Okay, so that's also, this is the time period of the angular simple harmonic motion. Do you understand? So when this electric dipole is in a stable equilibrium, so when you disturb this slightly, which means the angle theta is very small, it will make a simple harmonic motion, right? Angular simple harmonic motion. Okay, so done. So for that simple harmonic motion, what is the time period? So this is the time period, 2 pi square root of the moment of inertia divided by PE. Okay, so that's it. Do you understand? Okay, so that is one formula you have to remember. So the time period of the simple harmonic motion of this electric dipole, so that is given by this formula. Is that okay? Yeah. This time we have a non-uniform electric field. That means the electric field is a variable. So the force acting on the charge Q and the force acting on the charge minus Q, they don't have the same magnitude. That means they will not cancel each other. So there will be a net force, right? So that force is what we have to find. So in the case of uniform electric field, the total force is 0. Here it is a non-uniform electric field, so there will be a force. So that force we have to find. Alright, yes. Now, so if you remember from the work energy chapter, so du, right? So that is the change in potential energy. So that equals the negative of the work done. So what is the formula for work done? So force multiplied by the distance, so that is taken as dx, right? So force multiplied by the small distance dx. So this is the formula, so that you're supposed to know. Now from that we can write the value for force. So the force here is equal to, so this is minus du divided by dx. Now we have taken force to be in the direction of x-axis, right? So you need directional force, right? So only one direction. We have taken the particular case. So force equals minus du divided by dx. Okay, so that's it. Now we have the formula for this u, right? The potential energy. So that we are going to use here. So that equals, so minus d by dx of this potential energy. So that is the formula minus p dot e. Okay, so this is the formula for the potential energy. Okay, so that means simply, so this is P vector dot, so this is the derivative, right? dE vector by dx. So that's all. So this is the force. Okay, so that's all. So this is the force formula that we have to use when the electric field is non-uniform. Okay, yes. Now particularly when this dipole moment and the electric field are in the same direction, okay, so these two are in the same direction, then the dot product is simply the product of the magnitudes. Okay, so we can write in that case the force equals, so this is P multiplied by d by dx. So that's all. So this is the formula we are going to use to find the force due to a non-uniform electric field, right, on a dipole. Okay, so P So the dipole moment multiplied by the derivative of the electric field. Okay, as a particular case, when this is uniform, the electric field is uniform, that means it is a constant. So what is the derivative of a constant? That is 0. So the whole value becomes 0. That means the force is 0. So that is the last case we have done, right? So the force is 0 when the electric field is uniform, but this is the most general case. Okay, so that's all. So this is the force due to a non-uniform electric field. So the dipole moment multiplied by the derivative of the electric field. Okay, yes. Now if the directions are different, so you may have to use this formula. Okay, right, yes. So now, so this is one formula that you are supposed to remember, right? The force due to a non-uniform electric field. Okay, yes. So these are all the concepts that we have done in electric dipole. Let us use all these concepts to solve some questions. Okay, so be thorough with all these ideas before we start solving questions. Okay. The charges q, minus 5q and 4q are placed at the points 0, 0, 2, 0 and 8, 0 respectively. If P is the total dipole moment and the electric field at the point 101, 0 is given by 2kq divided by m multiplied by minus 1 by 25 cube plus 4 by 24 cube. Then here we have three charges q, minus 5q and 4q placed on x-axis. We have to find the total dipole moment and also we have to find the electric field due to this dipole. But it is not a dipole as such, right? Because it is not a combination of a positive and a negative charge of equal magnitude. But we can split that charge minus 5q into minus q and minus 4q. So one minus q can be combined with the charge q. So that will become one dipole. And similarly minus 4q and plus 4q, that will make another dipole. So there are two dipoles. We have to find the total dipole moment. So we have to find a vector sum of these two values, right? These two dipole moments we have to find separately and find the vector sum. Okay, so the total dipole moment. So the dipole moment P vector. So that is the total dipole moment. So dipole moment due to both these dipoles. So let us take one of these dipole moments to be say P1 vector. The other one is say P2 vector. So P1 is due to the first dipole having charge q and minus q. So what is the formula for dipole moment? So that is the distance multiplied by the charge. So charge here is q only. So q is the charge and multiplied by the distance. So the distance here is 2, right? Because this is at origin, the other one is at 2, 0. The distance between them is 2. So 2 multiplied by the charge. Okay. So the first dipole has dipole moment 2 multiplied by the charge q. Okay. But what is the direction? So the direction of the dipole moment is from the negative charge to the positive charge. Do you understand? That means from that charge to this charge, it is in the negative x direction. So that means, so the direction is, the vector along that direction is minus I cap. Okay, that is in the negative x-axis direction. So 2q is the magnitude and that is the unit vector in the direction of the dipole moment. Okay, done. So that is the first dipole. Okay, done. Now similarly, second dipole. Again same thing, the charge multiplied by the distance. What is the distance here? So in the second case, the distance is 2, 0 and then 8, 0. The distance between them is 6. So 6 is the distance multiplied by the charge 4q. So that will give you our required value. So 6 is the distance multiplied by the charge 4q. So that is the magnitude of the dipole moment. Okay. What is the direction? Now negative charge to the positive charge. So that means this direction, right? Positive x-axis. That means the unit vector in that direction is say I cap. Okay, so that's all. So that is the dipole moment of the second dipole. Now we have to simply add this. So this is 2q, this is 24. So 24 minus 2. So this is 22 iq I cap. So that's all. So this is the dipole moment vector. If you just need the magnitude, okay, if you just need the magnitude, you can take the magnitude of this. That is 22q. So that's all. So that is the answer. So the dipole moment due to both these dipoles, so that has value this one 22q. Done. Okay. Now we'll also find the electric field due to this dipole at a point say 101, 0. So that means we know the distance. So we will use the, again we can use the same formula for electric field for both the dipoles separately and then find the vector sum. Okay. Yes. Now so the electric field. So what is the electric field formula? So the electric field, the total electric field is the electric field due to the first dipole plus the electric field due to the second one. Okay, yes. So that has value. Yeah. So what is the electric field due to? The first one. So that has formula. So we have the formula for the electric field due to a dipole at a point on the axis. First of all, what is r? The distance between the dipole and that point. See, we have to take the distance always from the midpoint, okay? Not from any of these charges. From the midpoint, what is the distance? What is the midpoint? So this is 2, 0, 0, 0. So the midpoint is 1, 0. And that point is 101, 0. So that means the distance is 100. So which means r value is 100. Do you understand? So from 1, 0 to 101, 0. So the distance is r. So r value is 100. Do you understand? So what is the formula for the electric field? So that is 2k cube divided by, okay, r cube. R is 100. So that means it is 100 cube. Okay, done. So that is the electric field due to the first dipole, but that is only the magnitude. What is the direction again? So the direction is along the p value only. So the direction of electric field is same as the direction of the dipole moment for a point on the axis. That means it has the same value, say minus I cap. Okay, same direction as the dipole moment. Okay, minus I cap, done. Now similarly we will find the electric field due to the second dipole. So that has value, so same thing. So that is 2k, but the charge here is 4q divided by the distance square. Again from the midpoint you have to find the distance. But what is the midpoint of this 2, 0 and 8, 0? So that is 10, 0, 5, 0. So that is the midpoint, right? 2 plus 8, 10, 10 by 2. So 5, 0 is the midpoint. From that, what is the distance? So that is 101. So 101 minus 5, that means 96. So 96 is the value of r here, which means this is 96 cube. Okay, and the direction is I cap only, positive x-axis, so no problem. So that's all. So this is our required electric field. So we have to simplify this. Let us take the common factor. So what can you take out? So this is 2k cube. So this can be taken as a common factor, and then so this is 100 cube and this is 96 cube. So 4 cube can be taken out, right? So 4 cube. If you take out 4 cube, so that will become, I am writing only the magnitude now. So this is also I cap here, we just write the magnitude. So that is minus 1 divided by, so 100 cube, so 4 cube is taken common, so that means it will be 25 cube. And here, so 2k cube is taken out already, so it is plus 4 divided by, so 96, so we have taken out 4, so that means it is 24, so 24 cube. So that's all. So that is our required electric field magnitude. Okay, so this is the electric field vector. So but here we have written only the magnitude because magnitude of I is 1. So that's all. That is our required answer, the magnitude of the electric field due to both these dipoles. But this is what is given in the question. So we can compare this with what is given in the question, the electric field. So then we can get the value of this. Okay, so this is the value 4 cube. So that means the value of this m, that equals this 4 cube. So that means it is 64. Okay, that's all. So that is our required answer. Do you understand? So it is very simple. We find the electric field due to both these dipoles separately, but you have to take into account the direction, because here the charge, positive q is this side, negative q is that side. That means the electric field will be in this direction. Okay, no, or the dipole moment will be in the opposite direction. So in the next case, minus 4q and 4q, so that will be in the positive x direction. So that's all. And one more thing, we have used the formula for the short dipole here. Okay, we have used the formula for short dipole here. So this is the formula for short dipole. Okay, we will not use the general case, because so the distance r is 101. Okay, r 100. So 100 compared to the distance, okay, between the two charges, that is 2 r 6, so that is very small. Okay, we assume that it is a very short dipole because the distance between the two charges here is 2 or 6, that is very small compared to the distance 100. So that is why we have used the formula for short dipole. Suppose it is instead of 101, so if you have say some 10 or 8, so that means we can't use this formula, we have to use the general formula. Okay, this is the formula for short dipole because that distance is much bigger compared to the small distance 1 or 2, so that's why we've used this formula. Is that okay? So that's all. So this is the answer to the question, the value of m and also the total dipole moment. So that is this 22q. Okay. The total dipole moment due to the system of charges given in the figure is. Here also we have three charges, but they are not on the same line like the last question. So they are placed like this. So there is a charge Q, minus 2Q and Q. First of all, we have to make dipoles out of this, right? This minus 2Q can be split into two parts, minus Q and minus Q. So one minus Q can be combined with this charge Q. So that will form one dipole. Similarly, the other dipole with charges minus Q and Q. But these two dipole moments, they don't have the same direction. So one is horizontal, the other one makes some angle, say 60 degree with the horizontal. Okay, yes. Let us find the vector form of these two dipole moments separately and then find the sum. Okay, let us find the dipole moment. So P vector, that's a total dipole moment. That is the dipole moment of the first dipole. Similarly, second dipole. Okay, the first dipole, so let us find. So what is the distance? So the distance here is A. So A multiplied by the charge. So A is the distance multiplied by the charge, so AQ. So that's all. That is the magnitude of the dipole moment of the first dipole, and the direction from negative charge to the positive charge. So negative to positive, that means it is in the negative x direction. So this is minus I cap, that is a unit vector. Okay, so AQ minus I cap. Okay, done. So that is the dipole moment of the first dipole. Plus similarly next one. So the next one also has the same distance. Okay, the distance between the charges, so that is A. So that means A multiplied by Q, same charge Q. Okay, that is the magnitude, but we want a direction. So this direction is different. Okay, that makes some angle, say 60 degree with the horizontal. So that means you have to find the projection in the horizontal and vertical direction. We have to write the unit vector in that direction. Okay, so what is the direction of the dipole moment from negative charge to the positive charge? That means this direction makes some angle 60 degree with the horizontal. That means what is the projection in the horizontal direction? Cos 60 degree. Right, 60 degree with the horizontal. So that means cos 60 degrees. So that is the horizontal projection. That means cos 60 degrees I cap. Okay, horizontal direction. Similarly, the vertical projection. So that is sin 60 degree. Sin 60 degree vertical projection. So J cap. Do you understand? So this is the unit vector in the direction of the dipole moment. So cos 60 I cap plus sin 60 J cap. So that's it. Simplify, you will get the answer. That's all. So this will be. So AQ, so AQ can be taken out, so AQ is taken out, so it will become minus I cap plus cos 60 degree. So cos 60, we can write the value of that, so that is 1 by 2 I cap, and sin 60 degree, so that is square root of 3 divided by 2, so J cap. Okay, so that's all. Let's simplify this further. So this is AQ multiplied by, so this is minus 1 by 2 I cap, and then it is root 3 by 2 J cap. So that's also, that is our required dipole moment vector. Okay, if you just need the magnitude, you find the magnitude of this, that's all. So what is the magnitude of this P? So that equals, so this is a scalar, so AQ multiplied by the magnitude of this is square root of this square plus this square, right? Magnitude of a vector, right? Square root of A square plus B square. So this is 1 by 4 plus, and this square, so that is 3 by 4. So that will become 1. Okay, so 1, so that means simply AQ is the answer. So AQ is the required dipole moment. Okay, that's also, that is our required answer. Simply we found the dipole moment vector. Okay, dipole moment vector due to these two dipoles separately. Find the vector sum, so that will give you our required answer. Okay, so AQ is the answer. A short dipole has dipole moment P along x-axis with center at origin. Find the electric field due to this dipole at the points r, 0, 0, r and r, r. We have a short dipole here along x-axis whose center is at origin. Now we need to find the electric field due to this dipole at various points. So the first point here is on x-axis. That means the electric field due to the dipole at a point on its axis. Similarly, the next point 0, r, so that is on y-axis, that is the perpendicular bisector, and the third point is r, r, so that is some random point, so that makes some angle. Okay, so the point is known r, r, so that means we can find the angle also theta. So using that we can find the electric field at that point also. Let us find one by one. So the first one, E1 vector, is the electric field due to the dipole at a point on the axis at a distance r from the center. Okay, so that has the formula. So that is denoted by E1 vector. So electric field due to a dipole at a point on its axis, that is the formula 2kp divided by the distance, so that is r cube. So 2kp by r cube, that is the magnitude. What is the direction? So the direction of the electric field here is same as the direction of the dipole moment, because The point is on the axis. So that means, so that is in the positive x direction. So that has unit vector I cap. That's all. Okay, so that is the first electric field E1 vector. Similarly, the next one, but this time the point is on the perpendicular bisector. So that has formula. So this is the formula, Kp divided by the distance r cube. That's all. So this is the magnitude of the electric field at a point on the perpendicular bisector. Okay, but what is the direction? So we know that the direction of electric field at a point on the perpendicular bisector is opposite to the direction of the dipole moment. So that means, so the dipole moment is in the positive x direction. So this has direction opposite, right? That means the negative x direction. So the unit vector here is minus I cap. Okay, so on the axis, so they have the same direction. Okay, electric field and dipole moment. But here on the perpendicular bisector, the opposite direction. So minus I cap. Okay, done. So now we have to find the electric field due to the dipole at some random point. Okay, r comma r. So we need the angle theta, right? So what is the angle made by this radial line with the horizontal? So that is theta. So what is that angle? Because r comma r, right, that angle is 45 degree, right? So that is a straight line making angle 45 degree. So angle theta is 45 degree. Okay, so what is the distance r? But this time r is not the distance. So what is the distance here? So it is r comma r, 0 comma 0. So what is the distance? That is root 2 r, right? We can use distance formula to find root 2 r is the distance. Okay, so what is the E3 vector? So we will not write E3 vector directly because we have written formula separately, magnitude separately, and then direction also we found separately. So that means first we will write the magnitude of E3 vector. So that is E3. So that equals, what is the formula? Kp divided by r cube, right? Kp divided by r cube. So Kp divided by r cube. But what is r here? So r here is square root of 2 multiplied by r, right? You understand that distance. So that distance is root 2 r cube. So Kp by r cube, but r here is root 2 r. Okay, done. Okay. Multiplied by square root of 1 plus 3 cos square theta. So 3 cos square 45 degree. So this is the formula we have written. Remember, Kp by r cube multiplied by square root of 1 plus cos square theta. But theta here is 45 degree, that angle. Okay, done. So let us simplify this. So this will become, yes, Kp divided by, so this is root 2 cube. So that can be written as 2 root 2 r cube multiplied by cos 45. Cos 45 is 1 by root 2. So that means it is 1 by 2. So 3 by 2. So which means root 5 divided by root 2. Okay, so that's it. So this can be written as root 5 Kp divided by, so this is 2 multiplied by 2. So 4r cube. So that's all. So this is E3, which is the magnitude of our required electric field. Okay, yes. Now we'll also write the direction of this E3 vector, right? So the direction of this vector, okay, E3 vector. So we have written the magnitude, now we will write the direction. So that also has a formula. So the angle made by this E3 vector, right, so with the horizontal, so that has formula. So if you remember, that is theta, which is 45 degree here, the radial vector angle, so that is 45 plus tan inverse of tan 45 degrees divided by 2. Okay, so this is the formula for the angle made by that resultant vector E3 with the horizontal, right? Theta plus tan inverse of tan theta by 2. So tan 45, that is 1. So this is tan inverse of 1 by 2, and this is 45 degree. So that 45 degree can be written as tan inverse of 1, right? So we'll write this 45 degrees tan inverse of 1 because we know that tan 45 degrees, that is 1. Now we want to add these two, that's why we write it as tan inverse of 1. So let us add these two. So tan inverse x plus tan inverse of y, so that has a formula, right? So a little bit of math is involved here. So inverse trigonometric function, tan inverse x plus tan inverse y. Or we can also use the formula of the direct trigonometric identities like tan a plus b. What is tan a plus b? Tan a plus tan b by 1 minus tan a tan b. So or if you remember this inverse trigonometric formula, tan inverse x plus tan inverse y. So this is the formula. So that is tan inverse x plus y. So x plus y is 1 plus 1 by 2. So 1 plus 1 by 2 divided by 1 minus xy. Xy is 1 minus 1 by 2. So that is tan inverse of 3. So that means if this E3 vector makes some angle, say phi, with the horizontal, okay, then tan phi, tan of that angle is 3. Okay, so tan of the angle made by this E3 vector with the horizontal, so that is 3. Okay, yes. So this means tan theta value. So the value of tan theta equals 3. Okay, so that is the meaning. Okay, done. So that means we know the angle and we know the magnitude. So then we can find the vector form of E3. So E3 vector. So E3 vector equals the magnitude. So the magnitude is root 5 kp divided by, so this value, so 4r cube, that is magnitude, multiplied by the direction. Direction means what? The unit vector in that direction. So what is unit vector? So cos of this angle phi. So that is the horizontal component cos phi, and the vertical component is sin theta. Okay. So cos phi is the horizontal component and sin theta, sin phi. Okay, so that is the vertical component. Okay, so that is a unit vector in that direction. But what is the value of cos phi? We only know the value of tan phi, right? So phi, not theta, because theta is the angle made by the radial vector with the horizontal. But this total vector, the E3 vector, so that makes angle phi. Okay, that means it is theta plus alpha, right? So the total angle is phi. So that tan phi is 3. So but we want cos phi. So what is the value of cos phi? So we can use this triangle idea, right? Because what is tan theta? So that is the opposite side divided by the adjacent side. That means this value is root 10 by Pythagoras theorem. So that means, so we can find cos theta or cos phi. Cos phi is what? The adjacent side, 1 divided by root 10. Similarly, sin theta is 3 divided by root 10. So that's all, we can simply substitute that. So that will become, so root 5 kp divided by 4r cube multiplied by cos phi. Cos phi is 1 divided by root 10. So 1 tan I. So I cap plus 3 j cap divided by root 10. Okay, so this is cos phi value, 1 divided by square root of 10 and 3 divided by square root of 10. So that's all. So that is our required E3 vector. Now we can simplify further. So root 10 can be written as root 2, root 5. So 1 root 5 can be cancelled. So which is kp divided by, so root 2. So 4 root 2 r cube multiplied by I cap plus 3 j cap. So that's all. So this is the our required vector, E3 vector, that is the electric field due to the dipole at a point, right, r comma r. So that's all. So these are the 3 electric field vectors required in the question, right? The electric field due to the dipole on the axis, that is very simple, direct formula. On the perpendicular bisector, so that is also simple. But here, so this is some random point, okay, at some point r comma r. To find the electric field, we have to find the magnitude separately using this formula, and the direction also is found separately using this formula. Okay, these two are formulae that you have to remember. Okay, and some math is also there. So tan inverse x plus tan inverse y, so that is the formula. Okay, so just in case you've forgotten that formula, so what is the formula for tan inverse x plus tan inverse y? So this is the formula we have used here. So tan inverse of x plus y divided by 1 minus xy. So this formula is what we've used here to get this value. Okay, yes. So that's all. So that is our required answer, the electric field due to the dipole at some point. Okay, that's all. So that is the answer. The axis of a dipole of dipole moment P and moment of inertia I is inclined at angle theta to the electric field E. If released at this position, the angular speed when theta equal to 0 is. We have a dipole placed in a uniform electric field at certain angle theta with the electric field. Okay, it is released from this position, then it will have an oscillatory motion, right? When it reaches the horizontal position, that means angle theta becomes 0. So what is the speed, the angular speed we have to find? Okay, so let us find the angular speed. See, one method of doing this is, see, we have the expression for torque, right? Torque. From torque we can find the angular acceleration, because we have the formula. What is torque? The moment of inertia multiplied by the angular acceleration alpha. So just like force equals mass times the acceleration, so we can find the angular acceleration. Integrating that, we will get the value of the angular velocity, right? Because we have the formula, the derivative of velocity is the acceleration. Similarly, the derivative of the angular velocity, so that is the angular acceleration. So that is one method, but that is a little lengthy, right? So we will not do that method. We will use energy conservation, because we have this uniform electric field here, right? Conservative force. So energy is conserved. So the total energy at this position and total energy in the horizontal position, so these values are equal. Do you understand? So let us find the total energy. So here energy is conserved. So let us find the energy. What is the energy? Initial energy. So the kinetic energy, right? The potential energy plus the kinetic energy. So that is a constant value. Okay, so what is the energy? So what is the potential energy when the angle is theta? So we have the formula for that, right? So what is the potential energy? Minus P cos theta. So that is the potential energy when the dipole makes angle theta with the electric field. So minus Pe cos theta. Okay. Now what is the kinetic energy? Kinetic energy is 0, right? It is released from this position. So that means the kinetic energy at that point is 0. Okay. Now the final point. Okay. So when it is horizontal, what is the potential energy? So horizontal means what? Theta is 0. That's all. The same expression, minus Pe cos 0. So that's all. So okay, let me write as it is. So minus Pe cos 0. And then the kinetic energy. Okay, so the rotational kinetic energy, right? Not half mv square, right? So that is translation kinetic energy. Now we want the rotational kinetic energy. So that is not half mv square, but half moment of inertia I omega square. You understand? So just like half mv square for the translation rotation kinetic energy, here rotational kinetic energy half I omega square. That's all. So from this we can get the value of omega. What we want is omega, right? The angular speed. So that's all. Omega can be found from this. So let us simplify this. So if you take this P out here, so P multiplied by, so this is 1 minus cos theta. That equals, so half I omega square. That's it. So this will give you the value of omega squared. So that equals 2P multiplied by 1 minus cos theta divided by I. So that's all. This is the value of omega squared. So we can find the value of omega taking the square root. But 1 minus cos theta we can write 2P multiplied by, what is 1 minus cos theta? So using some trigonometric identities, 1 minus cos theta is 2 sine square theta by 2. So divided by, so this I. Okay, so that's all. So this is the value of omega squared. Now we will write the value of omega by taking the square root. So what is square root of this? So Pe divided by I. So square root of that. So that is Pe divided by I. Okay, done. Now square root of this is 4 sine square theta by 2. So if you take the square root, it will become 2 sine theta by 2. So that's all. So that is the required answer. The angular speed when it is in the horizontal position. Okay, so omega. So that equals the square root of Pe by I. So 2 sine theta by 2. Okay, so that's all. So that is the answer. The force due to the charge q placed at origin on a short dipole of dipole moment P placed along x-axis at a distance r is. Here we have a dipole along x-axis and there is a charge q placed at origin. Now due to this charge there will be some electric field, and due to this electric field there will be some force on the dipole, and that force is what we need to find. See, here the electric field is not uniform because the electric field due to a point charge, so that has formula kq divided by r square, so that depends on the distance, so it is a non-uniform electric field. We have written a formula for the force on a dipole due to a non-uniform electric field, so let us use that formula. Okay, yes. So here, so the electric field due to the point charge, the electric field due to the charge q, so that has the formula, so E equals, so kq divided by r squared, because the dipole is at a distance r from the point charge, so this has the formula kq divided by r squared. So that is the electric field due to the charge q at a distance r. Okay, done. Now what is the formula for the force due to a non-uniform electric field? So we have the force on the dipole. So what is the formula for the force on the dipole? So that has formula, so that is P multiplied by the derivative of the electric field, okay, d by dr. D by dx, here r is taken as the distance, so d by dr. E is known, so this is the value of E, so that if you simply differentiate, okay, so the derivative of that multiplied by P will give you our required force. That's all, very simple. So this is simply P multiplied by, okay, let me write it, so d by dr of this electric field kq divided by r squared. Okay, that's all. Let's find the derivative. So P multiplied by kq divided by r square. How to find the derivative? So these are all constants. R is the variable here. We can write it as r to the power minus 2, and if you find the derivative, that will become minus 2kq divided by r cube. So that is our required force. Okay, so the force equals, so minus 2kqp divided by r cube. Okay, so that's all. So that is the force due to the charge q on the dipole. Okay, so that's all. So that is the answer. But we'll also do this question by another method. See, we found the force due to the charge q on the dipole, but instead we can also find the force due to the dipole on the charge q. But they'll both have the same magnitude, right, by Newton's third law. So the force due to one object on the other object is same as the force due to the other object on this object. So they have the same magnitude, only the direction is reversed. So we will find the force due to the dipole on the charge q. So that will have the same magnitude as the force due to the charge on the dipole. Okay, so this is another method of doing this question. So alternative. So let us first find the electric field. So the electric field due to the dipole. So we are going to find the force. So for that, first we will find the electric field. So what is electric field due to a dipole at a point on the axis, because origin is on the same axis as the dipole moment. So that is at a distance r. Okay, so that means what is the electric field here? So that is the formula. So the electric field here equals, so 2kp divided by r cube. So if you remember the formula for the electric field due to a dipole at a point on the axis at a distance r. So that is the formula 2kp divided by r cube. Okay, done. Alright, so this is only the electric field, but we want the force. So let us find. So force on the dipole. So the force on the dipole. So we know the formula for force. So force equals a charge multiplied by the electric field. Okay, so charge is known q, and that multiplied by this electric field will give you our required answer. So that is simply multiply this by the charge. So that is 2kpq divided by this r cube. Do you understand? So this is the force exerted by the dipole on the charge. So similarly, the force exerted by the charge on the dipole has the same magnitude but opposite direction. Okay, so that means the force on the dipole. Force on the dipole. So this is force on the charge q. Now force on the dipole is the negative of that. So minus f. So that equals a minus 2kpq divided by r cube. Okay, so that's all. So negative of this, the magnitude has the same value, right? So 2kpq divided by r cube. So that's it. So that is the required answer, right? So the electric field is not uniform here. So that means the force has this formula. Okay, so we can either use this formula or you can use that method to find the force due to a point charge on a dipole. Okay. A light rod lying along x-axis is hinged at origin. The charges minus q and q with equal mass m are fixed on the rod at 2, 0 and 4, 0 respectively. If the rod is rotated by a small angle theta, the time period of the oscillation is. So there is a rod here hinged at one end, and also there are charges q and minus q fixed on this rod at some distance, right? 2 units and 4 units. Okay, now we have a rod and also some charges. So this is the dipole, right? So these two are opposite charges, q and minus q. So this is the dipole. Now this rod is in the equilibrium position. That means horizontal position, right? Stable equilibrium. Now it is slightly disturbed, so it will have an oscillatory motion. So we have to find the period of this oscillatory motion. Okay, so let us use the formula. We have derived a formula, if you remember, the time period of the oscillatory motion. So t equals, so 2 pi square root of the moment of inertia divided by PE. So this is the formula we have derived for the time period of the oscillatory motion of this dipole. Okay.
But this formula is only when the dipole is rotated about the midpoint.
Actually, it doesn't matter whether the dipole is rotated about the midpoint or about some other point, the torque will remain the same. See, take this example. So this is the axis of the dipole. So there is a charge minus q and q. So the distance between the dipole, so that is 2a, and the total distance, so this length is taken as say r. Okay, so this is the point about which the dipole is rotated. Okay, so that makes say angle theta with the horizontal. Okay, now what is the torque here? On this charge q, what is the formula for torque? The force multiplied by the perpendicular distance. So force in this direction, so the force multiplied by the perpendicular distance. So the total distance is r, but we want the perpendicular distance, perpendicular component, so multiply by r sine theta. But the total force here is q multiplied by e, right? Charge multiplied by the electric field, and then the perpendicular component of the distance, so that is r sine theta. Okay, so this is the torque on the charge q. Similarly, we'll find the torque on the charge minus q. Okay, so that is minus qe. Okay, minus qe multiplied by, so that distance, but that distance is from the point to that charge, the distance is, total distance is r minus 2a. So that is r minus 2a multiplied by sine theta. You understand? Now if you simplify this, qe r sine theta, here also minus qe r sine theta, so that gets cancelled. So we'll simply get, what do you get here? So qe 2a sine theta. So that means, so this 2a multiplied by q, so that is the dipole moment, so p sine theta. So that is the formula for torque we have derived when the axis of rotation is through the midpoint. Okay, the same formula, so it doesn't matter so what is the axis of rotation, so the value will remain same, the torque remains same. So when the torque is same, so that means it will have the same time period. You understand? So time period is calculated from the torque only. So p sine theta, that is the torque, even if the angle or the axis of rotation is not through the midpoint. Okay, yeah, so this value will remain same. So t, the time period, equals 2 pi multiplied by square root of I divided by p. That's all. So same formula, so nothing, we have to simply directly substitute these values. So what is I? The moment of inertia, so that equals 2 pi square root of, so we have to find the moment of inertia of this charge, say q. So what is the moment of inertia? So that is mass m, so mass multiplied by the distance square. Okay, the distance is given here, so that distance here is 4, right? 4 is the distance, so 0 0 4 comma 0, so that means 4 is the distance, so mass multiplied by 4 square, mass multiplied by 4 square, plus similarly, so the moment of inertia of the other charge, so same mass but the distance is 2, so that means the mass multiplied by 2 square. Okay, yes, divided by p. So p is the dipole moment, so that is the distance, so the distance multiplied by the charge, so the charge is q, but the distance between the dipoles, okay, the distance between the two charges, so that has value 2 multiplied by the charge q and then the electric field E. So that's also, that is our required answer. So simply we get, so 2 pi square root of, this is what, 4 plus 16, 20 m divided by 2, so that means it is 10 m divided by QE. So that's all. So this is our required answer. So the time period of this oscillatory motion. Okay, that's all. So what we understand from here is that, so this point of rotation, okay, that need not be the midpoint. So it can be any point, but the time period or the torque, that will remain the same. Okay, so that's all. So the answer to the question is simply this one, 2 pi square root of 10 m divided by QE. Okay. Two short dipoles with dipole moments P1 and P2 along x-axis are separated by a distance r. The force of interaction between them is. Here also we need to find the force on a dipole, but not due to a point charge like the last question. Here we need to find the force on a dipole due to another dipole. We have two dipoles here, but they have the same axis. We have to find the force on one of these dipoles due to the other one. Okay, so you find the force on that dipole due to this dipole, or you can find the force on this dipole due to the other dipole, because they have the same magnitude. Okay, so the directions may be different. So let us find the force on one of these dipoles due to the other one. So let us first find the electric field. So the electric field here is not uniform, because we have the formula for the electric field due to a dipole, but that is dependent on the distance r, so it is non-uniform electric field. So we have to use the variable force formula, right? So P multiplied by dE by dr. So let us use that formula to find the force due to one dipole on the other dipole. First let us write the electric field. Okay, so electric field due to one of these dipoles. So electric field due to, say, dipole 1. Okay, so one of them is taken as dipole 1, so this one. Now electric field due to that dipole at a distance r on its axis, so that has the formula. So the electric field here is simply, so 2k P divided by R cube. So that is the formula for electric field due to a dipole at a point on its axis at a distance r. Okay, electric field is known. Once electric field is known, so we can use the formula to find the force. So the force on the dipole, say dipole 2, so the other one, so dipole 2, so that force has formula. So the force equals, so this is the formula, right? So P multiplied by dE divided by dr. Okay, so this is the formula for force when the electric field is non-uniform. But here this P is the dipole moment of the second dipole, so that is taken as P2. Okay, P2 is the dipole moment, but here this P is the dipole moment of the first dipole, so that is taken as P1. You understand? So these two have two different dipole moments. So that means this is P2, P1. Okay, done. Now this E you have to substitute here. That's all. Okay. So let us do the differentiation here. So this is P2 multiplied by d by dr of this value E. So that is 2k P1 divided by R cube. Let's find the derivative of this one. So P2 multiplied by, these are all constants, R to the power minus 3. R to the power minus 3 has derivative. So that is 2k P1 multiplied by R to the power minus 3, that is derivative minus 3 divided by R to the power 4. So that's all. So that is our required answer. So that is minus 6k P1 P2 divided by R to the power 4. So that's all. So this is our required force on one of these dipoles due to the other dipole. Okay, so minus 6k P1 P2 divided by R to the power 4. So very simple, we found the electric field due to one dipole. So from electric field we can find the force using this simple formula. Okay, so that is our required answer. Okay. Two short dipoles of dipole moment P1 and P2 making angle θ1 and θ2 with x-axis respectively are separated by a distance r. The force of interaction between them is. This is the most general case of interaction between two dipoles. In the last question we had two dipoles but both were facing the same direction. But this time we have one dipole making some angle θ1 with the horizontal, the other one makes angle θ2. We have to find the force due to one dipole on the other one. We almost use the same idea. So the formula is the force equals, so that is the dipole moment multiplied by the derivative of the electric field. So that is P multiplied by the derivative d by dr or d by dx, so depending upon what you take as the distance. So this is the formula for the force, but that is only when the directions are same. This P, the dipole moment, and this electric field, so these two are same, only then we can use this formula. But here these two are different, so we have to use the vector form. This is P vector and also this is electric field vector. Because the directions are different, so we have to use this formula. So take the dot product of this. Okay, yes, so this is the formula for the force due to one dipole on the other dipole. Okay, now what is this P? This P is the dipole moment of the second dipole. The force is on the second dipole, so that means this is P2. Okay, so that is the force, that is the dipole moment of the second dipole. But the electric field here is due to the first dipole. Okay, so that means let us denote that by say E1 vector. Okay, so that's it. So now we have to find this P2 vector separately, and then similarly E1 vector, and then substitute these values here. Okay, let us find P2 vector. So P2 vector is the vector form of the dipole moment due to the second dipole. What is the scalar? The magnitude, that is P2 only, multiplied by the vector along that dipole moment. So that makes angle θ2 with the horizontal. So that means, so we can take the projection in these two directions, horizontal component and vertical component. So what is the horizontal component? It makes angle θ2, which means cos θ2 is the horizontal component multiplied by I cap, horizontal direction. Okay, I cap. Similarly, it has a vertical component, so that is sin theta. So sin θ2 j cap, vertical component, j cap. Okay, done. So we have found the value of P2. Okay, P2 vector. Now similarly, we need this E1 vector, which is the electric field due to the first dipole. So E1 vector. Now the electric field here is at some random point, not on the axis, not on the perpendicular bisector. Here the electric field due to the short dipole at some random point, okay, making some angle θ1 and also at a distance say r. So we have to find we have to use the general formula for the electric field due to a short dipole. Do you remember the formula? See, it is like this. There is a dipole making angle theta 1, another dipole makes angle theta 2. So let us take the charge to be minus q and q, because this is the direction of the dipole moment, so minus q and plus q. So due to these two charges, there will be some electric field. So q, that will have electric field in this direction because positive charge, and due to this negative charge, there will be electric field towards itself, right, in this direction. Okay, but the net resultant, the resultant electric field will be somewhere here, somewhere between this. Okay, so that is the electric field. Alright, so this direction and this direction, so that is the resultant. That means it will have two components, one in the horizontal direction, one in the vertically downward direction. Remember, vertically downward direction, because this is the resultant. So what is the horizontal component? That is the radial component. Do you remember we have written the formula for the electric field due to a short dipole at any point having two directions? Okay, one is the radial component, one in the perpendicular component, right? So one is in the perpendicular direction, one in the radial direction, but the radial direction here is the direction of x-axis only, that means I cap. So what is the component in the radial direction? So that is this formula. So 2kp divided by the distance, so r cube multiplied by cos theta. Okay, now we are finding the electric field due to the first dipole, so that means it is p1. Okay, due to the first dipole. Similarly, the angle is theta 1 multiplied by I cap. So this is the formula for the radial component of the electric field due to a dipole. Okay, radial component. Similarly, the perpendicular component, so that is formula. What is formula? So that is, so minus here because negative y. So this is the perpendicular component. So radial component is in this direction, perpendicular component is downward direction. So minus j cap. So minus. So the perpendicular component is, so that is formula kp1 divided by r cube. So no 2 here, kp by r cube sine theta. That means sine theta 1 j cap. That's it. So this is the electric field vector, okay, due to the first dipole. Done. Now we have to find the derivative of this with respect to r. Okay, rest of these values are constant, k, p1, theta 1, all these values are constant. The only variable here is r. That's all. So let us write it again. E1 vector equals, you can take out the common factor, so kp1 divided by r cube multiplied by, so 2 cos theta 1 I cap minus sine theta 1 j cap. So let us find the derivative of this with respect to r. So that means dE1 vector divided by dr. So that equals, so all these are constants, so only this derivative you have to do. So r cube, so that is same as, so that is in the denominators, r to the power minus 3. So r to the power minus 3 has derivative minus 3 r to the power minus 4, r3 divided by r to the power 4. Rest of the values same. So kp1, so this is 2 cos theta 1 I cap minus sine theta 1 j cap. So that's also, we have found derivative of the electric field with respect to r. That means this we have found. Similarly, P2 is already found. Now we have to find the dot product. Alright, so the scalar product of these two vectors. Okay, so let us find it. So this is like our okay, something like equation 1. This is equation 2. We have to take the dot product of these two vectors. Okay, let us find the dot product. So this implies, that is the force F equals, so let me write again, so P2 vector dot the dE vector divided by dr. So that equals, we found both. So all these are scalars, right? So P2 minus 3 r to the power 4 k P1. So that if you multiply, so you will get minus 3 k P1 P2 divided by r to the power 4 multiplied by this dot product, I cap with I cap only. So cos theta 2 multiplied by 2 cos theta 1. So that will be 2 cos theta 1 cos theta 2. Okay, so that is the I dot I, so that is 1. Similarly j, so sin theta 2 multiplied by minus sin theta 1. So that means simply, so minus sin theta 1 sin theta 2. So that's also, that is the answer. So this is our required the force. Okay, So that's all. So if you simplify and write it, so that's all, nothing much can be done about it. So this is minus 3k p1 p2 divided by r to the power 4 multiplied by, so this value 2 cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. So that is the answer. That's it. Now as a particular case, if theta 1 and theta 2 both are 0, what will happen? So these two will become horizontal. So these two dipole moments are in the horizontal direction. So that is the last question. What will happen in this formula? If you substitute theta 1, theta 2 both 0, so what will you get? So this will become 0. Sin theta is 0, sin 0, because cos 0 is 1, which means simply 2. So 2, that means it is minus 6k p1 p2 divided by r to the power 4. So that is the result we derived in the previous question. Okay, minus 6k p1 p2 divided by r to the power 4. So that is a particular case. Do you understand? When theta 1 and theta 2 are 0, both become horizontal. Okay, but here it is the most general case. Okay, now if you remember this, so we can directly use it in questions. Suppose if this is vertical like this instead of horizontal, if it is vertical, this dipole moment is in the vertical direction. So that means theta 1 will be 90 degrees. Okay, so whatever direction, whatever angle is given, so we can directly substitute and find. Do you understand? Or we can do these steps to get the answer. Okay, so this is the force due to a dipole making some angle theta 1 with another dipole making a different angle. Do you understand? So that's all. So this is the answer to the question, the force due to one dipole on the other dipole. Okay. That's about electric dipole. With that, we have completed our first part of electrostatics, where we have learned electric charge, Coulomb's law, electric field related things, electric flux, Gauss's law, and electric dipole. In the second part of electrostatics, we have electric potential energy, electric potential, conductors and dielectrics, and the rest of the things related to capacitors. Alright, let's keep learning.